The broadcast is now starting. All attendees are in listen-only mode.
Good morning. Thank you for joining us for another SLCan presentation webinar series. Presenting today is Blair Antcliffe from the University of British Columbia. The presentation today is on leveraging demand-controlled ventilation, a success and retrocommissioning story. Blair is an energy engineer with the Energy Conservation Group of UBC Energy and Water Services. He's been at UBC for 6 years, during which time he's worked on projects including heat recovery chiller installations, coordinating retrocommissioning on countless buildings, and spearheaded UBC's implementation of a fault detection and diagnostics platform. Blair holds a BEng from the University of Toronto, an MEng from UBC, and the Certified Energy Manager designation. So I'm going to hand this over to Blair right away. If you have any questions, please type them into the question box and we will get back to them at the end of the presentation. All right, Blair, take her away.
Okay, thanks, Kevin. And I'm gonna say right off the hop that Kevin Shalast has been somewhat involved in this project, and right away, this is not an endorsement of the Air Acuity system, though I have some slides from Air Acuity, and it happens to be the brand that we've used, but other demand control ventilation systems, I'm sure, are capable of doing this. So just a little bit, this is UBC on a beautiful sunny day. It's a really nice place to be. But when I look at this photo personally, one of the things I notice is all of these fume hood exhaust stacks. And kudos to the photographer, they definitely hit another 14 stacks that I happen to know are behind that tree. And a big focus of our energy management at UBC has been on labs. And so you see from the bubbles here, the typical total energy use intensity of some offices, classroom, libraries, those are on average about 250 kilowatt hours per square meter per year on campus, whereas laboratories on average are upwards of about 400. And this is just a selection of some of our worst ones. In a typical air handling unit for a classroom or office, and I'm sure that for a lot of people attending this, I'm preaching to the choir, but we've got return air that comes into the air handling unit. A bunch of it is exhausted. A bunch of it gets recirculated. That recirculated air is mixed with outside air and is discharged into the spaces being conditioned. In a laboratory, however, and we're able to look at a return air CO2 in a lot of cases and control that and modulate the amount of outside air that we bring in to maintain air quality in the space. In labs, however, outside air gets brought in, spit straight into the spaces, and any return air gets vented straight out through the roof. So there's no opportunity to recirculate the air and reuse the energy from the space. And it's oftentimes a much greater volume of air that needs to be conditioned. Of course, the reason for this is that we have to protect all those lab users from themselves. And so here's kind of what it looks like. On the top, we've got the typical supply fan speed from one of our lecture theaters, and we can see it. Oh, the other reason that labs use so much energy, is that we're able to turn off air handling units for other spaces at night, whereas for labs, those same air handling units run 24 hours a day. So on top is a typical lecture theater, on the bottom is a typical laboratory air handling unit. And the biggest reason that we do this, well, it's to maintain air quality, and we need to maintain the 6 to 8 air changes per hour. All the standards do say something a little bit different, but this one that's highlighted is sort of the most common rule of thumb. However, there are different standards nowadays that allow, as highlighted, active sensing of air quality in individual labs. And so what this allows is some sort of system that senses when there's a contaminant released into the laboratory space, and then we can ramp up the air change rate. This is stolen straight from our acuity, but a side benefit of this demand response is that in a spill event, concentrations are actually kept at concentrations are kept lower for longer, because with a high air change rate, there's a lot of air movement and it happens to disperse contaminants very quickly. It's a bit of a complicated, I think it speaks for itself in a big way, but it's great to have demand responses is sort of the gist of it. So we have to have some sort of system that, in a sense, sniffs the air. In our particular case, we're using an air acuity system, and let's see if I can, I don't remember how to do my height. Oh, there's the spotlight. So we've got all these duct probes where the air leaving the individual labs has this probe, it gets sensed, a little air sample is taken to what air acuity calls their air data router. It's basically a fancy pneumatic switching box. And then from this air data router, it goes to a sensor suite, which takes a measurement of the air contaminants. It compares against a outdoor air, or sorry, there's the outside air baseline to give what the relative concentration of contaminants is in the lab. That is in turn sent to our building management system, and we can ramp up or down the ventilation. Oh, come on, come back, controls. And so what the BMS will do is it does a high select between the thermal demand, or the kind of minimum airflow based on the fume hoods, or air acuity. So one might say, hey, I need 200 liters per second. The hoods might say, well, we need 250 liters per second. And maybe this demand control ventilation says, oh, we only need 150. So it goes with the 250 liters per second option. So the first building where UBC installed this is the Michael Smith Laboratory. And here's some quick facts about it. It's a pretty typical lab system. It's got a decent thermal EUI of 186 because we do have a heat recovery system recovering heat from our laboratory exhaust air, but that electrical EUI is quite high. And the savvy among you might find that the floor space percentages, in fact, do not add up to 100%. And that's because a lot of spaces like hallways or washrooms or the atria, those are not allocated spaces. So at a high level, here's the business case that we're looking at. Almost a $500,000 project cost. We got a good chunk of incentives from Hydro and Fortis. And we're looking to save just shy of $57,000 per year, which would give us a payback of 4.6. Keeping in mind that there is an annual recurring maintenance cost of $14,000 per year, and air acuity for that cost will replace all of the sensors in all of the sensor suites twice per year. So it's great that it's getting maintained. That does chew into the savings a decent chunk. So we installed it April 17th. That's the magic date, 2019. And right off the hop, we could see that particularly overnight, we're saving a whole lot of air. What we're looking at here is, I think this one is hourly average total supply air volume to laboratory spaces. So yeah, right off the bat, we turn it on, we're saving 4,500 liters per second. This has a lot going on, but on the top is electrical baseline versus actual power, electrical power hourly, and on the bottom is thermal. And so we can see that particularly, where's my pointer again? particularly overnight, we're saving quite a bit of power. A little bit less so during the day, but we expected that going in because the system is doing that high select. If there's still thermal demands driving airflow rates, those aren't going to have been affected. On the thermal side, you know what, we're saving quite a bit of the time, so we're doing well here. So we let that run for a little bit. After a couple of months, we look at the Q-sum savings, so accumulated thermal and electrical energy savings, and it's not enough. It's really not enough. We're on track for less than half of what we expected. It's not doing great. So this is towards the end of the summer. I start going in and investigating. Okay, what's going on? Why are we not saving what we think we're going to save? So here's the first thing that I found. The red line is what's actually going on for this particular lab, Lab 351. The blue line is what's being commanded by the BMS. And so right off the top, we can see that, well, the airflow is supposed to be going way down to whatever that is, 160 liters per second, but it's staying put at like sorry about that, the headphone turned off. The actual is staying put at 350 liters per second. And through quite a bit of investigation, this little dastardly fellow popped up. And it turns out that this is just a clamp on the actuator shaft, and it is a hard mechanical stop limiting the air valve position. And this took quite a while to find. Part of the reason is that these are legacy air valves from Phoenix Controls, and documentation on them is pretty sparse. So we fixed that. It didn't solve everything. Turns out that on the control board of these Phoenix boards is also this little min clamp. And what you're looking at there, that blue piece is probably about the size of my thumbnail. It's tiny. And this is also an electronic stopper as well. Again, the documentation was sparse, and I can thank Kevin Shalast here because he's the one who eventually found it in some esoteric documentation where it was mentioned in passing in some setup documentation. So finally, we fixed that, and hey, what do you know? It's getting us another 3,000 liters per second. And so we're looking October through November. You can. It took 2 visits by the Aqua Air crew to fix all of this, and you can see those straight in the data. So here's the first visit, and then here's the second visit. And sorry, my text is in the way, but we're getting more savings. Now there's a bit of a dip through October, November, and we can talk about that, but maybe the trajectory of the thermal savings is improved a bit, but it's still not great. We've barely nudged the dial here. So we start kind of looking the other way. What about max airflow? We've done pretty well to drop the bottom out. But our daytime max flow rates are still up near where they were. So remember again, right. So that spot where the baseline flow rate goes back up, we had a server issue, and Windows Update kind of locked up the server and things stopped working, and so that was a couple of weeks we had to get that fixed. So recall earlier I mentioned that the BMS does a high select between the air change rate for the hoods or the thermal load or the demand control. Well, we can't really control what the users are doing with the hoods in the space, nor can we really control whether or not they're spilling contaminants in the space. The one thing through BMS that we can control is the thermal load. Sorry that I keep on switching there. So one of the things that we tried is to reduce the discharge air temperatures from the air handling units. So from a fixed set point of 18 degrees, and we'd let it float a little bit more. Because one of the things that we found was that a lot of spaces that we're trying to cool were just demanding this 18-degree air kind of all the time. So if they're trying to get the temperature down to say 20 degrees, it's much more effective to do that with 16-degree air or 15-degree air as opposed to 18-degree air. So we let this drift a little bit. The other thing that I found was that in a lot of these kind of thermal zones, this is all one thermal zone because the air is allowed to travel in between these spaces. These doorways are typically just kept open all the time, except for the door to the hallway. But there are 4 different temperature sensors on the wall. There's 4 different supply air valves supplying conditioned air to the space. And if I look just at this particular room, what I was finding, I forget what the date is for this, but they're trying to keep, some of them were trying to keep the temperature below the red line, and some of them were trying to keep the temperature above the blue line, and they're just constantly fighting each other. And so in BMS, we kind of went back, did a review of all of the space temperature set points, and made sure that there was nothing crazy in there so that nothing would fight each other. Now we've standardized to a 20-degree heating set point and a 24-degree cooling set point in the spaces. And hey, what do you know? This is a pretty good success after reducing the cooling demand. Oh yeah. So we're doing better, we're still chipping away. Finally asking the question, okay, we can't control what the users are doing, but maybe we can actually reduce the airflow demanded by the hoods, because again, I have to thank Kevin for this. When we go and we do the math for a single room, even if all the hoods are closed, even if it's thermally satisfied, we're still in this particular space getting 5 air changes per hour, just because those fume hoods have a huge airflow requirement when they are closed. Because as you can sort of see here, it's minimum 140, and then that ramps up as occupants open up those fume hoods. So maybe we can reduce that down even. So this is where Kevin Celeste comes in, pointing out this new ANSI fume hood ventilation standard, where instead of just being based on the surface of the working area inside that fume hood, it functionally is treated as its own little room and getting its own air change rate. And if we use this standard, we instead can go down from 5.1, recall, to 3.7 air changes per hour. And so we did that, got AquaAir to come in, reset all these fume hoods, got them all retested. And it's not a huge amount, but you know what? 11,700 to 10,400, that's almost another 10% savings. So here's the overall effect of the efforts from March. Well, so April 17th, I guess April 17th is the magic date when AirQD was enabled. We've got the Windows update where everything kind of goes haywire. We did the rescale procedure. That's when we found those stoppers. We did the air handling unit supplier temperature reset. In February, limited zone temperatures to make sure that they weren't fighting each other. Reduced fume hood minimums, so did the fume hood air change rate procedure. However, the building was reoccupied in May. They put together a COVID plan and started doing research again, so that's why we can see the daytime spiking again. But overall, we're going from a daily average of 21,500 liters per second down to about 14,000 liters per second. So that's about a 35% reduction in average airflow in the building. So if we look again at that Q sum, in fairness, the thermal energy savings does not look great, but the electrical savings is absolutely going gangbusters. If we look at the second year, our first year of operation goes again from April through to April, and that was we're calling that a learning period within our office, and hoping that the second year goes much better. The second year, well, I'll show you on, where's my keyboard? The next slide. The first year wasn't great, but we're looking at almost doubling our projected electrical savings for the second year, which is making up for the not really getting the thermal energy savings. And so we are still just about hitting the payback period that we want. It should be noted that these cost savings do not include the $14,000 per year maintenance fee, because it's a budgeting thing. We're counting that maintenance fee separately from the energy cost savings. So I've got some key takeaways here, and wow, I thought I was 40 minutes, but I'm only 20 because I forgot that this was the cut down version. Sorry, the headphone turns off every 10 minutes, and for some reason, it doesn't think it's being used. So every project is just a tool in the toolkit. So what I mean by that is we installed an air QED system. Installing the equipment doesn't get you the savings. That certainly didn't get us the savings. The air QED system is something that, or demand control ventilation, is something now that we can leverage to find the savings that we're looking for. It's not some silver bullet. There is no silver bullet. I think everybody knows that. No project is a replacement for building recommissioning. What having this demand control ventilation has done is it's really highlighted to us all of the spots where our building has been deficient, where we haven't properly maintained the systems. It's pointed out broken air valves all over the place. We've had to replace countless poppet valves because our pneumatic systems have not been up to snuff. We've been finding the savings because we have leveraged this system to do the recommissioning. Like, really, the recommissioning is where we're getting the savings. Sorry, Kevin. And then also, hurry up and get a fault detection and diagnostic system. I recognize that I'm very, very biased because I'm the one who has functionally set up UBC's fault detection and diagnostic, but a lot of this hinged on being able to analyze BMS trend data very quickly, very effectively. FD&D goes from me looking at this is the BMS view of the AHU serving the lab spaces in this building. I'm pretty good at BMS, but this is incomprehensible. It goes from this to this. This is so much easier to understand. At a glance, you can see the trends, you can see what the operation of the whole unit. It's great. And FD&D really found every graph that you saw in this presentation is from our FD&D platform. And then that's it. That's it from me. 25 minutes. I will answer any and all questions, and Kevin can.
Thanks, Blair.
Kevin can help me out with that.
Yeah, thank you very much. That was a great presentation. So we'll go through some questions. If you have any, type them into the question box. And if there's anything we can't get to immediately, we can definitely chat with you after the fact. So the first question we have is from Kevin Shea. For the fume hoods, what air change in the fume hood did you settle on, and did you conduct a hazard analysis to determine that air change rate. Presumably, that refers to getting involved with risk management or EH&S. Blair, do you want to start with that? And I recall meetings.
Sure, I'll start with it and I'll tag you in. Yes, it did involve RMS, the department formerly known as RMS. It's I can't even remember what they're called now. But yes, we got permission from RMS to do this. They normally do certify their fume hoods annually. So part of the agreement was that we would change the airflow rates and then recertify all of the fume hoods. That was their caveat for letting us do that. As for how to decide on the air change rate or what the airflow rate would be, that was actually Kevin Shalest. He came with his little laser measurer and determined what the air change rate should be, and then based on that, what the linear velocity should be of the fume hood. Is that right, Kevin? I don't recall.
Basically, yeah, the standard does offer a range that can be added or that can be applied, and there are reference material that have been used. For example, UCI has done some extensive work on fume hood minimums. So the bottom line is to get approval and to review this with your risk management department, and so they understand what changes or updates are being made. And often it's kind of done hand in hand, as it was with UBC, on working with the EH&S experts to find out what to settle on in terms of the air change rate for the hood. Now, I don't believe we went down to the full extent of the standard. We had to settle out on somewhere in between, I believe, between 200 and 250 air change rates.
Yeah, I think it was something like that. I think we did towards the lower end, but I insisted on having a bit of a buffer.
So next question we have is, can someone utilize a fault detection system if they don't have a full-time staff to review it and take action on everything? How do smaller owners work with this?
That's a great question. That's a very good question. I believe that a lot of the FD&D providers have solutions for that. I think a lot of the time what they do want to provide is not just the software system, but the engineering to go along with it and the monitoring to give you sort of a monthly report. Here's the issues that we found. Here's what you should address in your system. And if you're able to swallow the cost of that, then great. If you're not able to swallow the cost of that, then maybe hopefully you can get kind of a stripped back version. But when I say get good at using the FD&D, I do mean like without having to go to a third-party engineering services. Like if you're able to use your BMS system, you should be able to figure out how to use an FD&D system, and it'll allow you to go in and identify anomalous behaviors, whatever the platform is. We've toyed with. We happen to have SkySpark on campus, but we have also tried out CopperCube and Clockworks, and I don't even know. I think I've seen most of them because I worked with BC Hydro on kind of reviewing the industry offers. There's lots of good options out there. The big part is to be able to look at BMS trends over a long period of time, I think, and compare those trends over discrete time intervals, and or to write some sort of script or some sort of find where you can find when those BMS trends are not just visually out of whack, but also hey, tell me all the times when the air handling unit discharge air temperature was greater than 21, and it can maybe spit that back out to you instantly. And so what these a lot of the time can help you do is not spend hours upon hours in Excel looking for these trends.
All right.
I don't know if that answers the question.
I think that covers it. Again, like if there's any supplemental questions that we can't get to today, we can definitely get to them after the fact. However, we do have one more here from Kevin Shea. How did you guys decide on the first building to try out the air quality monitoring system? What are some key decision-making factors to consider if you have a range of building options?
Also a fantastic question. So when Aqua Air, I think you guys came to us first, actually, kind of with the sales pitch. Do you remember, Kevin?
What we eventually, I believe what happened, we actually did a site-wide or a campus-wide assessment of potential energy savings across several buildings. And
yeah, but how did we let you do that? How did you get your foot in the door?
I don't recall. That would be before my time. Regardless, I think we basically went through a variety of buildings and laid it out in front of your energy management team.
Yep.
Might have been someone else beforehand. And basically take a look at what the potential savings and also capability with the current system to install a system for demand-based ventilation. And
yeah, it was 7 buildings.
Correct. And I think a lot of, as to your presentation, it's incumbent that your building is capable of utilizing such technologies. So we needed to know that we could be stable at lower air change rates and maintain pressurization and directional airflow. And I mean, a lot of it really comes down to, and Blair, give your 2 cents on this too, just doing it hand in hand with as a team effort, because there's a lot of factors that come into play as Blair demonstrated during his presentation that impact how the system operates after the fact and the potential savings.
Yeah, I'd say for somebody else looking at doing this, some of the key considerations might be age of the system. I probably wouldn't recommend to somebody to do it in a building that has pneumatic controls. And Kevin, I think you might agree, having now gone through this headache, because really the sort of the feedback isn't as robust, and the number of spots where something can go wrong is much greater. That's not a hard and fast, but pneumatics were definitely a pain in the butt through this whole process. There's a kind of a physical space constraint where the air acuity, at least again, I'm speaking just in terms of air acuity, the air acuity sensor suite can't be more than some set distance away from the furthest probe. So that might be a consideration. In general, you'll obviously get more savings from a building that is performing worse, which is a weird thing to say, but if you don't have a heat recovery system, then every cubic foot or cubic meter of air that you're providing into the space has a higher associated cost. So that might be a way of looking at it, is to say, how much do I have to condition the air in order to provide it to the space, and then put this into the building that has the highest value of that. Because that's where we did look at 7 different buildings, and this was the pilot, but this is the only one where the demand control ventilation system even remotely made sense. The other lab spaces, frankly, were too high performing already to justify this system, which is a bit of an unfortunate kind of ironic twist.
That's actually a good point, Blair, and I can't recall for sure, but I believe part of the upgrade, the cost associated, were to upgrade the Johnson-based system as well.
Yeah,
So,
that's true.
so to Blair's point, the newer systems could be more perhaps quote unquote dropped in, which would certainly help with the project costs. So
Yes, that's true.
it is a
And
balance. Yeah.
we have pursued this in two other. Well, we have installed it in one other building since, which wasn't an option at the time of the initial study, because and again, I'm less tapped into this stuff, but at the time of the original study, animal care facilities weren't an option, but the standard, and I forget who sets that standard, but domain control ventilation wasn't an option for animal care, and now it is, and so we've put it into an animal care facility.
Yeah, correct.
And then I think pharmacy will be the same. That's I think you're working with James on that. I think that's the CL3 lab.
Not particularly for that one, although I believe the standard you're referring to is the Canadian Council for Animal Care. And
yeah, that's right.
Those guidelines have recently been updated. Again, perhaps another takeaway on the side. I guess I don't see any further questions. Again, if anyone has anything else to ask, by all means, please contact Blair, and we'd be happy to get back to you. Blair, do you have any closing comments or anything else at this time?
Nope.
Right.
Thanks for having me. Thanks for the questions. Yeah, the domain control ventilation it's great. It's a pillar that I think we're going to continue to use in the future. I think probably for all new construction lab buildings, we will put some version of domain control ventilation in. I think that's another spot where you can really manage the costs, because a lot of the costs are kind of getting somebody to pull the micro duct, or for simplicity, let's call it the pneumatic lines, and install sort of the equipment associated with the DCV system. And if you can just kind of tie that in with construction costs, then I think it becomes a no-brainer.
All right. Well, thank you very much. And we'll join everyone on the next SLCan webinar. And take care and stay safe. Thank you.
Keep going.